Welcome to the electronics lab, everyone. As your professor, I've spent about 2 decades right here within these walls. I've watched generations of engineers discover the absolute magic of circuits for the very first time. And today, I am incredibly excited to walk you through an explainer of one of the most critical experiments of your entire engineering journey, diode applications. Now, this isn't just some dry theoretical exercise. We're talking about the hands-on foundation for literally everything you're going to build in the future.
Before we even touch a single wire, let me ask you something. Why is the simple diode universally considered the Swiss Army knife of electronics? I can tell you from my 20 years of teaching, this tiny little component is the most versatile, flexible piece of hardware you will ever wire up on a breadboard. It's a safety valve, it's a converter, and it's an incredible signal shaper, all rolled into one.
Okay, let's dive right into our lab outline for today. We'll start with AC to DC rectifiers, then move on to the smoothing capacitor. After that, we'll look at diode clipping circuits, and we'll wrap things up with diode clamping circuits. I promise we'll break all of this down logically. Now, before we get our hands dirty, let's quickly review the gear we'll be sharing across all these setups. We'll need a DC power supply, an AC frequency generator, resistors, diodes, capacitors, and a center tap transformer. Oh, and of course the oscilloscope. Just a quick pro tip from my years in the lab, please remember to actually turn on the oscilloscope before you start taking measurements and wondering why there's no signal. Happens every semester. All right, let's get into Section 1 AC to DC rectifiers. It is time to tame that current. This is where the taming really happens. We are going to take that wild alternating current, the stuff that constantly flips direction, and force it to flow one way to give us useful direct current. Looking at the circuit connection for the halfway rectifier, you'll see we just have one single diode. Remember the golden rule here. A diode only lets current pass in one direction. So when the AC wave comes crashing through, this little guy just completely chops off and blocks the negative half of that wave. Your job is to wire this up, and more importantly, accurately draw both the input and output waveforms. You'll see exactly how that bottom half just vanishes.
Moving right along to Section 2, the smoothing capacitor. Let's perfect our DC.
So we've got our waves flowing in one direction now. But here's a question for you future engineers. What happens if we just leave those continuous, bumpy pulses alone in our full-wave rectifier without adding a smoothing capacitor? Is that really perfect DC? Now, what's really interesting about this comparison is seeing exactly how we fix that. In a standard full-wave rectifier, the output is just a series of continuous bumps. It looks like a mountain range. But when we add a little secret weapon, a capacitor wired in parallel, everything changes. That capacitor charges up and then slowly discharges, effectively smoothing out that bumpy, rolling output into nice, clean, perfect direct current.
Next up is Section 3, diode clipping circuits. Let's start shaping the wave.
We're shifting gears now from power conversion into a totally different engineering concept, signal shaping. So what exactly is clipping? As the definition breaks down, it's essentially using a conventional diode to cut off, or basically chop, a specific portion of an alternating waveform. I want you to know exactly what you're hunting for on your screens today. You'll be looking for a familiar wave, but with its top or bottom sharply sliced right off. Take a close look at the 4 different circuit configurations for diode clipping. Pay attention to how just flipping the direction of the diode or throwing in a variable DC power supply completely changes where that wave gets chopped. We are precisely controlling exactly where we swing the sword and cut that signal. To make sure you nail this, we're going to follow the experimental procedures exactly. First, connect your circuit elements. Then, you're going to gradually vary that DC power supply from 0 to 5 volts and draw your input and output waveforms while keeping the signal generator value fixed. After that, we reverse it. Vary the signal generator voltage from 0 to 5 volts while keeping the battery value locked. Carefully observing and logging your comments as those voltages change is the absolute core of real engineering work, so pay close attention to these steps. Let's look at our final part, Section 4. Diode clamping circuits. Time to shift the signal. In this final setup, we're going to witness a completely different behavior that creates an awesome contrast with the clipping experiment we just did. Clamping, in a nutshell, is the process of using a diode to shift, or literally lift, an entire waveform to a different DC level. But here's the absolute most critical part. We do this without changing the wave's shape. With clipping, we chopped it. Here, we're taking the wave exactly as it is and just migrating it completely to a new level on the screen. And this brilliantly illustrates the core difference you absolutely need to highlight in your lab reports. Clipping cuts off a portion of the wave's peak or trough. It intentionally distorts the wave. Clamping, on the other hand, faithfully preserves the wave's entire shape, but simply shifts its baseline DC level up or down.
Let's break down this circuit connection together. The absolute key addition here, the thing that actually makes the clamping effect happen, is the capacitor placed right before the diode. This capacitor essentially charges up and acts like a secondary battery, which is what forces that entire wave to shift. And just like we did with the clipping circuits, remember to vary your 0 to 5 volt supplies so you can watch that shifting effect change right before your very eyes.
Across all our stations today, whether you're working with rectifiers, clippers, or clampers, I always want you to remember this. The oscilloscope is your window into the invisible world of electronics. Accurately drawing those input and output waveforms is the true key to mastering the slab and truly understanding diode behavior. Trust those waveforms. To wrap up our explainer, I want to leave you with a provocative question. Where do we actually use all these complex clipping and clamping circuits? Well, the answer is that they are inside the very smartphones resting in your pockets right now, and frankly, in almost all modern tech. Don't just look at these experiments as drawings in a lab manual. These are the fundamental building blocks that power our world. I hope you've got a solid grasp on these concepts now. All right, head over to your benches and let's start measuring.